Today, we are going to learn a very important concept in the ESR spectroscopy, that is the coupling in ESR spectroscopy. Okay, you have already learned about the coupling in the NMR spectroscopy. In NMR, the coupling is due to the nucleus interaction, right? Nucleus interaction. Because a nucleus will have a magnetic moment, okay, and it will interact with the magnetic moment of another nucleus, and this is the reason why you are getting the split pattern in the NMR spectrum, or that is the reason why you are observing the coupling in NMR spectrum, or spin splitting in NMR spectrum. In the same way, you can expect this type of coupling in the ESR spectrum also. You already know that the ESR spectrum is being generated because there is an unpaired electron in the molecule or radical or the species which is under investigation, right? There will be an unpaired electron. There can be one unpaired electron or there can be more than one unpaired electron. Okay, in all these cases, the species is going to give the ESR spectrum. Okay, so if this is the case, there are two types of coupling possible in NMR. One type of coupling is due to the electron-electron interaction. Electron-electron interaction. It means the magnetic dipole moment of one electron will interact with the magnetic dipole moment of the other electron. Okay, means these two tiny magnets will interact each other, and that is the reason for one type of coupling. So let me classify the reasons for the coupling. The one reason for the coupling is the electron-electron interaction. Okay, interaction. And if this is the reason for the coupling in the ESR spectrum, that is the electron-electron interaction, means the magnetic dipole moment of the electron, one unpaired electron, interact with the magnetic dipole moment of the other unpaired electron, then this is the reason for the fine structure observed in ESR spectrum. Okay. And there is another reason for the coupling observed in the ESR spectrum. And you already know that the electron has a magnetic dipole moment because electron has a spin and it is a charged particle also. So there will be a magnetic dipole moment mu e. And this electron is surrounding the nucleus, right? Electron is surrounding the nucleus. And you already know that the nuclei might also have a magnetic dipole moment. Many of nuclei might have a magnetic dipole moment. For example, you know that the nucleus of the hydrogen atom has a magnetic dipole moment, or the nucleus of the hydrogen atom acts like a bar magnet. So the nucleus will also have a magnetic dipole moment. For example, you are considering the nucleus of the hydrogen atom. The nucleus of the hydrogen atom is nothing but a proton. Therefore, I can write the magnetic dipole moment of the hydrogen nucleus is MP, that is the magnetic dipole moment of a proton. So there are two magnets, an electron magnet and a nuclear magnet or a proton magnet. And these two magnets can also interact each other, or these two magnetic dipole moments can also couple. Okay, so the coupling is due to this reason also, that is due to the nucleus electron coupling, electron nucleus coupling, okay, or interaction. And if this is the reason for the splitting in the ESR spectrum, then that is called the hyperfine structure. So you can see two types of splitting in the ESR spectrum, that is the fine structure due to the electron-electron interaction and the hyperfine structure due to the electron-nucleus interaction. First of all, let us learn about the hyperfine structure. That is due to the interaction of the electronic magnetic dipole moment with the nuclear magnetic dipole moment. Okay, and this is analogous to the splitting that you are seeing in the NMR spectrum. In the NMR spectrum, the one nucleus, we are considering one nucleus, and this one nucleus is then coupling with n other nuclei. Okay, so n other nuclei are there, n nuclei, etc., 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 to n nuclei. Okay, this nucleus coupled with this nuclei. And if the number of these coupling nuclei are n, the splitting of this resonance, splitting of the resonance due to this nucleus, the first nucleus, will be n plus 1. Means this nucleus has n neighbors coupling, and then the splitting of the peak or due to this nucleus will be n plus 1. That is called the n plus 1 rule. You already know this from the NMR spectrum. This is same in the case of the hyperfine structure in the ESR spectroscopy also. Means you have an electron, this is the electron. Let me draw that electron in the red color just to understand that that is the electron. Okay, and that electron has a electron has a magnetic moment. And now this electron can interact with the nuclei having the magnetic dipole moment. This is a nucleus with a magnetic dipole moment, another nucleus with the magnetic dipole moment, then like that, etc., etc., to n nuclei with the magnetic dipole moment. So this is an electron, but all these are nuclei. Okay, so this electron will interact with the nuclei, n nuclei. So if n nuclei are interacting with the electron under consideration, the splitting in the ESR spectrum will also be n plus 1, same as the case of NMR spectroscopy. So if you are considering if you are considering one electron, and that one electron is interacting with the one nucleus, okay, then what will be the split pattern? Since there is only one nucleus, it will be n plus 1, that is equal to 1 plus 1, that is equal to 2. Means the ESR spectrum generated due to this electron will be split into 2, means you will see a doublet. If there are two nuclei, then you will see that it is 2 plus 1, that is equal to triplet. Means the ESR spectrum generated by this electron will be split into 3. Or the peak generated by this peak will be split into 3, and so this is a triplet. Okay, so this is how the splitting occurs in the hyperfine structure of the ESR spectrum. Now, if you are comparing the coupling constant of the hyperfine structure of the ESR spectrum with the coupling constant that we are observing in the NMR spectrum, okay, we are going to compare the coupling constant that we call the coupling constant as A ESR, and then we are comparing the coupling constant that we are observed in the NMR spectrum. Okay, and you can see that the coupling constant that we are observing in the ESR spectrum is much bigger than the coupling constant that you will observe in the NMR spectrum. Okay, so the coupling constant in the ESR spectrum is much bigger than NMR coupling. So there are some reasons behind this. There are some reasons behind why the ESR coupling or the hyperfine structure coupling constant is much larger when compared to the coupling constant observed in NMR spectrum. We will examine these reasons. One reason is that in the case of ESR spectrum, the electron can approach the nucleus much more closely. Okay, that is one reason why we have a large coupling constant in ESR, is because the electron can approach the nucleus more closely. Means, see, in the case of the NMR, the coupling is due to the nucleus interaction. But there is some restriction for the nuclei to come together. because these nuclei are already surrounded by an electron cloud, okay, and there will be bonds between the nuclei, and so there are some restrictions that the nuclei cannot come so close each other. So the nuclei are coupling at certain distance, right? One nucleus is sitting here and another nucleus is sitting at a certain distance from that nucleus. That two nuclei cannot come very close together. So they are acting at a distance. But in the case of the ESR spectrum, okay, here we have a nucleus, and the surrounding the nucleus there is the electron cloud. So this electron cloud is spread up to the nucleus, okay, the electron cloud is spread up to the nucleus, means the electron can have a much closer approach to the nucleus, okay, electron has a much closer approach to the nucleus, and because of this short distance interaction, the coupling will be much larger in the case of the ESR spectrum. So this is the reason electron can approach the nucleus more closely. This is one reason why the ESR coupling constant is much bigger than that of the NMR spectrum. Okay, and the second reason is that we will examine the second reason. The second reason is that the magnetic dipole moment of the electron, let me call this as mu e, magnetic dipole moment of the electron, is much bigger than the magnetic dipole moment of the nucleus. Magnetic dipole moment of the nucleus. Let the nucleus that we are considering is the hydrogen nucleus, then the nucleus is nothing but the proton. So let me represent the magnetic dipole moment of the nucleus as MP, it is the magnetic dipole moment of the proton. So you can see that the magnetic dipole moment of the electron is much bigger than the magnetic dipole moment of the proton. What does it mean? The electron is a much better magnet compared to the proton magnet. Means electronic magnet is much better than or much stronger than the proton magnet. We will examine this quantitatively. We already know that the magnetic dipole moment mu is equal to q by 2m into root of s into s plus 1 into h divided by 2 pi, where q is the charge of the particle that we are considering, m is the charge mass of the particle, s is the spin quantum number of that particle, h is the Planck's constant. Okay, we already learned this equation in the previous class. This is a magnetic dipole moment of the charged particle with charge q and a mass m. Let us consider the nucleus and electron as the charged particle, even if it is not a very good approximation, because we cannot take the electron or proton as charged particle. That is very important. They are not purely particles; they have wave character. So that is just for the simplicity of the calculation, let us forget about their wave nature. We just consider them as the point charge particles. Okay, so this is the magnetic dipole moment. So let us calculate the magnetic dipole moment of the nucleus, and means the proton and the electron. Okay, you already know that the mass of electron me is equal to, what's the mass of the electron? 9.1 into 10 raised to minus 31 kilogram. That's the mass of the electron. Okay, so I can write it like almost, instead of 9.1 I can write 10. Okay, it is almost equal to 10 into 10 raised to minus 31 kilogram. That is equal to 10 raised to minus 30 kilogram. That's the mass of an electron, 10 raised to minus 30 kilogram. Okay, approximately. And what about the mass of the proton? Mass of the proton is equal to 1.67 into 10 raised to minus 27 kilogram. That's the mass of the proton. So let me write it like it is approximately equal to 1 into 10 raised to minus 27 kilogram, because I just took 1.67 is approximately equal to 1. Okay, so I can write it like approximately equal to 10 raised to minus 27 kilogram. Okay, that is 10 raised to minus 27 kilogram. So what about the mass of the proton? So we can write it like mass of the proton is equal to 10 raised to minus 30, 10 raised to minus 30 into 10 raised to 3 kilogram, right? That is equal to 10 raised to minus 27. 10 raised to minus 30 into 10 raised to 3. And 10 raised to minus 30 kilogram is nothing but the mass of the electron. So let me write it as mass of electron into 10 raised to 3. Okay. So the mass of a proton, it means that the mass of the proton is almost 1000 times higher than the mass of the electron. Mass of the proton is 1000 times higher than the mass of the electron. MP is equal to 1000 ME. Okay, that is what we already know. So now let us calculate the magnetic dipole moment. Magnetic dipole moment. Magnetic dipole moment mu of the proton or mu p or mu of the nucleus, hydrogen nucleus, is equal to Q divided by 2m. Q in this case is E. E is the charge of the proton. Remember, proton and electron has the same charge. The magnitude are same. Only the difference is in the sign. Okay. So we are going to calculate the absolute value of the magnetic dipole moment. Means we are just to quantitatively calculate the magnetic dipole moment. So it is E divided by 2 into MP. What is MP? MP is equal to ME into 1000. So instead of writing MP, I can write 1000 into ME or ME into 1000. ME into 1000. Right? So that is Q divided by 2m into root of S into S plus 1. So S is equal to half, because protonic spin is equal to half into half plus 1 into h divided by 2 pi. That is the magnetic dipole moment of the proton. Okay, the absolute value of the magnetic dipole moment of the proton. And what about the magnetic dipole moment of the electron? Magnetic dipole moment of the electron. Magnetic dipole moment of the electron, mu e, is equal to charge of the electron. That is also E. The absolute value of the charge is E, right? So E divided by 2 m. M in the case of electron is me into root of S into S plus 1. Electronic spin is half into half plus 1 into h divided by 2 pi. Okay, so we can write it like, see, now we are going to the magnetic dipole moment of the proton expression. So let me take some part of this equation, this much part, E divided by 2 me into half plus 1 into h divided by 2 pi. Okay, and this is equal to E divided by 2 m into half plus 1 h divided by 2 pi. What is that? That is the magnetic dipole moment of the electron, right? So the magnetic dipole moment of the proton, magnetic dipole moment of the proton is equal to this one, E by 2me into root of half plus 1 into 2 pi. That is equal to mu e, and in the denominator we have 1000 also, 1000. It means that, okay, it means that the magnetic dipole moment of the proton, magnetic dipole moment of the electron, mu e, magnetic dipole moment of the electron, mu e, is equal to mu e divided by 1000. Therefore, magnetic dipole moment of the electron is equal to mu p into 1000. Right? We just cross multiplied this like this. So magnetic dipole moment of the electron is 1000 times the magnetic dipole moment of the proton. That is what I said in the beginning itself. Electron has a much bigger magnetic moment compared to the proton. Okay, and it means that the electrons are much better magnets than the protons, or electrons are much better magnets than the nuclei, right? And because of this reason, the much better nuclei will couple with a much stronger value, right? Much stronger value. This is the reason why the ESR hyperfine coupling constant is much larger compared to the NMR coupling constant. So we have analyzed two reasons here. One reason is that the electron can approach the nucleus more closely, and so there will be a better interaction between the electron and the nucleus compared to the nucleus-nucleus interaction in NMR. The second reason is that the electron is a much better magnet compared to the proton, and the electronic magnetic moment is 1000 times the protonic magnetic moment. And because of these two reasons, we will observe a much larger coupling constant in the hyperfine structure of the ESR spectrum. Okay, now let us consider the ESR spectrum of the hydrogen radical. Okay, hydrogen radical. It means it is hydrogen atom. Hydrogen atom has a nucleus, that is the proton, and this proton is surrounded by an electron, right? If you are considering just the Bohr model, it's a simplified model. Okay, so if you are considering like that, then it has a nucleus, and surrounding the nucleus there is an electron. Okay, this is a hydrogen atom, or we can call it as hydrogen radical also, because this electron is unpaired. It is not paired with any other electron. Okay, so if you are considering the hydrogen radicals hyperfine structure, okay, what you will observe? So hyperfine structure is due to the ESR spectrum is due to the single electron in the hydrogen atom, and the hyperfine structure is due to the interaction of the single electron with a nucleus, right? And here the nucleus is proton. Okay, therefore what will be the hyperfine structure? And since there is only one proton, the hyperfine structure will be equal to 1 plus 1, that is equal to 2. Means you will get a doublet. You will get a doublet if you are checking the ESR spectrum of the hydrogen atom. Okay, so you will see like this, a spectrum like this. See, these are derivative spectrum. That is why you get like this. The ESR spectrum, we usually take the derivative spectrum, and these two represents the hydrogen. These two split pattern means it is the two peaks of a doublet. Okay, and if you are checking the coupling constant, means the distance from one of the peak from one peak to the other peak within the doublet, that distance is 0.05 Tesla. 0.05 Tesla. Okay, this is the coupling constant in the case of the hydrogen atom. Okay, and this 0.04 Tesla, 0.05 Tesla is equivalent to what? Equivalent to how many megahertz? We can just calculate it. Yesterday we learned that 0.34 Tesla is equivalent to, what is that? Do you remember? 0.34 Tesla is equivalent to 9528.482 megahertz. We learned this in the previous class. It means that it is approximately equal to 9500 megahertz. Okay, this is the approximate value. And if this 0.34 Tesla is equivalent to 9500 megahertz, and we can calculate 0.05 Tesla is equivalent to how many megahertz, right? It means 0.34 Tesla is equivalent to 9500 megahertz. If it is so, 0.05 Tesla 0.5 Tesla is equivalent to what? Okay, that is equal to if you are calculating this, then it is equal to 1400 megahertz. It's approximately 1400 megahertz. See, this is the coupling constant in the hyperfine structure of the ESR spectrum. And what do you think about this coupling constant? 1400 megahertz. What was the coupling constant that you were observing in the NMR spectrum? You already learned the NMR coupling constant. And what was the value that you have already learned in the NMR spectrum? You have already seen in the NMR spectrum for the coupling constant. Perhaps you might have seen a coupling constant of maximum of 2 kilohertz. 2 kilohertz. This was the maximum coupling constant that you have seen in the NMR spectrum. Compared to this 2 kilohertz, 1400 megahertz is very big, right? So you can see that the coupling constant that you are see in the hyperfine structure of the ESR is much bigger than the coupling constant that you will see in the NMR. That is what we were discussing 5 minutes ago, right? Means since the electron can approach more closely to the nucleus, and since the electronic magnetic moment is much bigger than the proton magnetic moment, we already learned that the coupling constant that we will see in the hyperfine structure of the ESR spectrum will be much bigger than the coupling constant that we will observe in the NMR. That is what we can see here. The coupling constant that we will see in the hyperfine structure of the hydrogen atom is 1400 megahertz, and it is much bigger than the largest coupling constant that we can see in the NMR spectrum, which is equal to 2 kilohertz. Okay, so we have already proven that fact. And now, if you are observing the ESR spectrum of most of the organic molecules or common organic species, it can be radicals most often, right? Then only you will get the ESR spectrum. And if you are observing the coupling constant in most of the organic molecules, you will see a coupling constant of 2 to 20 megahertz. 2 to 20 megahertz. This is what you are seeing in common organic molecules. Okay, now you can compare this coupling constant with the coupling constant that you observed in the ESR spectrum of the hydrogen atom. In the case of the hydrogen atom, you observed a coupling constant of 1400 megahertz. What is the coupling constant that you are observing in the case of common organic molecules? That is 2 to 20 megahertz. So the coupling constant in the hyperfine structure of the common organic molecules is much less than the coupling constant that you are observing in the case of the hydrogen atom itself. Okay, so we are comparing the ESR coupling constant of the hydrogen atom with the organic molecule. Here the coupling constant is much less. What will be the reason? Okay, what will be the reason for why the common organic molecules are giving the much smaller coupling constants? Okay, there are some reasons for that. First, the first reason is that the unpaired electron can move over several atoms. Okay, in the common organic molecules, why they are giving the ESR spectrum? Because those organic molecules will have an unpaired electron. Okay, and this unpaired electron in the molecules are not confined to a single nucleus. The unpaired electron in the nucleus is not confined to a single nucleus. But in the case of the hydrogen atom, this unpaired electron is confined to only one nucleus, because hydrogen has only one nucleus. So the entire electron is confined to only one nucleus, or the entire electron is surrounding one nucleus. But if you are taking an organic molecule, for example, you are taking an organic molecule with 3 or 4 nuclei like A, B, C, D, all these are nuclei, okay, and you are considering an unpaired electron in this molecule, and that unpaired electron may be residing in a molecular orbital which is spreading over all these nuclei. The molecular orbital is delocalized over almost all the atoms in the molecule, okay, or several atoms in the molecule. It is not like the atomic orbital. Atomic orbital will be confined to only one nucleus, but the molecular orbital will be spread over many nuclei or many atoms in the molecule. So this single electron, the radical electron, is moving over this entire orbital covering many nuclei, right? Okay, so the share of each nucleus, share of the single electron for each nucleus will be much less when we are comparing the hydrogen atom. In the case of the hydrogen nucleus, It has a maximum share. The share of the electron is 1 because the maximum electron density or the entire electron density is surrounding only one nucleus. Here the single electron density is surrounding many nuclei, and therefore the share of each nuclei will be less than 1, or the share of each nucleus will be much less. Okay, and this is the reason why common organic molecules will have much smaller coupling constant compared to the hydrogen atom. Okay, so if the electron share is less, what will happen? The electron share is less, then only a less density of electron will be available to interact with a particular nucleus. So the coupling constant will also be less. It means that the interaction is less, only less electron density is there to interact with a particular nucleus, means interaction is less, therefore the coupling constant will also be less. So the first reason is that the unpaired electron can move over several atoms. Unpaired electron can move over several nuclei. Okay, this is the first reason. Now again we are going to quantify the reasons. Okay, and the second reason is that is connected to the first itself. The coupling constant A, the coupling constant A is proportional to the electron density at a particular nucleus. We are considering the coupling due to a particular nucleus, and that coupling constant will be proportional to the electron density at that nucleus. We already learned that the electron density at a particular nucleus will be much less than in the case of the hydrogen. So each nucleus will have only a fraction of the electron density, and whatever may be the coupling that we are observed due to the coupling due to a particular nucleus, that coupling will be proportional to the electron density at that particular nucleus. Okay, so coupling constant A is proportional to the electron density, and in other words we can write A is equal to a constant R into rho. Here A is the coupling constant. This is coupling constant. This is coupling constant, and rho is the electron density. Electron density at the nucleus that we are considering, and R. What is R? R is equal to A divided by rho, means coupling constant divided by electron density, or in other words coupling constant per electron density or coupling constant per unit electron density. We can say like that, right? So we can call R as the intrinsic coupling for unit density. Intrinsic coupling for unit electron density. Okay, this is R, intrinsic coupling constant for or coupling for unit electron density. Okay. Therefore, if we want to calculate R, the intrinsic coupling for unit electron density for a particular nucleus, R is equal to the observed coupling constant divided by the electron density rho. Okay, so this is the intrinsic coupling for unit electron density. And now we can calculate the R value for the hydrogen atom. Okay, hydrogen atom or hydrogen radical. We already learned that the observed coupling constant from the spectrum of the hydrogen atom is 0.05 Tesla. This is the experimentally observed coupling constant. Okay, 0.05 Tesla means A is equal to 0.05 Tesla divided by rho. Rho is the electron density. Okay. And what is the electron density of the electron density around the hydrogen nucleus? That is equal to 1, because the entire electron density is for only one nucleus. Okay, so the electron density is equal to 1. That is the maximum value of the electron density. Electron density is 1 means the 100% of the electron density is surrounding that particular nucleus. Okay, so in the case of R, in the case of hydrogen atom, R is equal to 0.05 Tesla. Okay, so R in the case of hydrogen atom is 0.05 Tesla. We will use this R value in many calculations that we are going to follow. Okay, and now we can use the information that we have obtained so far in order to examine the spectrum of the methyl radical CS3 methyl radical okay. And if you are observing the ESR hyperfine structure of the methyl radical, what type of splitting you will be observing? To know that, you have to count the number of hydrogen nuclei. How many hydrogen nuclei are there? 3 hydrogen nuclei are there. Therefore, n is equal to 3. So n plus 1 is equal to 3 plus 1, that is equal to 4. It means that the ESR spectrum generated due to this electron, that will be split into a quartet. It will be split into a quartet. Therefore, if you are observing the hyperfine structure of the methyl radical, you will see a quartet, and it will be like this. And if you are observing the intensity ratio within this quartet, it will be in the ratio 1:3:3:1. And all these peaks will be equally spaced. All are equally spaced. Okay, my drawing is not that good. That is why you may think like it is not that equally spaced. In fact, all the peaks are equally spaced. And if you are measuring the distance between the two peaks, okay, that is the coupling constant, and in this case the coupling constant is 2.3 millitesla. 2.3 millitesla. And what was the coupling constant that we observed in the case of the hydrogen? It was 0.05 Tesla. 0.05 Tesla. And here we are seeing 2.3 millitesla. And 2.3 millitesla is much smaller than 0.05 Tesla. That is what we already learned a couple of minutes ago. Means most of the organic molecules or common organic molecules will have a much smaller coupling constant compared to the hydrogen atom. Okay, that we already learned. Now you see that just by an example. Okay, so this is 2.3 millitesla, and therefore we can calculate the electron density from this one. Let us calculate the electron density. The electron density rho is equal to A divided by R, right? Electron density rho is equal to A divided by R. We already have this equation here. Rho is equal to A divided by R. Okay. So let us calculate the rho. In our case, A is the coupling constant. In our case, the coupling constant is 2.3 millitesla. That is 2.3 into 10 raised to minus 3 Tesla divided by R. R is equal to, what is the value of R for hydrogen nucleus? We have to give the R value for the hydrogen nucleus here, because here the electrons ESR peak is coupled due to hydrogen nuclei. 3 hydrogen nuclei are there. Okay, the coupling is due to the hydrogen nuclei, so we have to give the R value of the hydrogen nuclei. What is the R value of the hydrogen nuclei? 0.05 Tesla. So let us substitute 0.05 Tesla here. Then we will get the electron density at a single hydrogen atom. And this value is equal to 2.3 into 10 raised to minus 3 divided by 0.05 is equal to 0.046, and that is equivalent to 4.6%. What does it mean? The electron density at a single hydrogen nucleus, electron density around a single hydrogen nucleus in the methyl radical is 4.6%. The methyl radical is like this carbon is there, three hydrogens are there, right? Three hydrogens are there, and this is a planar, and there is a single electron also, and this single electron is spread over the entire atoms, okay, means spread over all atoms. And if you are observing, or if you are measuring the density of this single electron around a single hydrogen, the density of this electron around single hydrogen, that density is 4.6 percentage. Okay, this is the density of this single hydrogen at the hydrogen nucleus. And if you are observing the density of this radical electron at the other hydrogen, that is also will be equal to 4.6 percentage. The same thing you are doing with the third hydrogen. You are observing the electron density, means radical electron density at the third hydrogen, that will also be equal to 4.6 percentage. Okay, and the remaining electron density will be on the carbon. Okay, so what is the electron density? Electron density at carbon. Electron density at carbon is equal to maximum electron density, that is 100 percentage, minus the electron density at the 3 hydrogen nuclei, that is equal to 3 into 4.6, and that is equal to around 86 percentage. Okay, so electron density at the carbon is 86 percentage. Means if you are checking the electron density of this single radical electron at the carbon, and the carbon will have the maximum share, 86% of the radical electron density will be at the carbon. It means that if you are trying to observe this radical electron, okay, if you are trying to observe this radical electron 100 times, you are doing 100 experiments to observe this radical electron. You just suppose that you are precisely measuring the, you are precisely determining the position of the radical electron. Quantum mechanically it is difficult, you know the uncertainty principle. Okay, so but you just think that you are able to locate this radical electron in every experiment, and you are conducting 100 experiments. What will happen? In 86 experiments, you will see that the radical electron is somewhere around the carbon. Okay, in 86 experiments, you will see that the radical electron is somewhere around the carbon, and in other 14 experiments, okay, in other 14 experiments, you will see that the radical electron is located somewhere around the 3 hydrogen atoms. So you are conducting 100 experiments, 86 times you will see the single electron near the carbon, and other times you will see the single electron at some other hydrogen atom. Okay, this is the meaning of that. The electron density at carbon is 86 percentage. Okay, so we have obtained a very fantastic idea of the electron density or the electron density distribution, the radical electron density distribution over the molecule from the ESR spectrum. That's very important chemical information, right? Because you know that when an organic molecule is reacting with a positive reagent, what the positive reagent will like to do? The positive reagent will be looking for the locations in the molecule where there is maximum electron density, right? So you can simply predict from here that the positive electron, the positive reagent will be attacking the carbon from this one, right? It will be looking at the carbon. So this is what we can observe from the ESR spectrum. So you can measure the ESR spectrum of some organic species and locate where is maximum electron density, and you can just predict where the positive reagent is going to attack. So that's a very important chemical information. Okay, so in ESR spectroscopy is fantastic in that sense. Now let us move on to another example, that is the benzene radical. Benzene radical, C6H6 radical. Okay, benzene radical. And here the ESR spectrum due to this radical will be split into 7, because we have 6 hydrogen nuclei. Therefore, 6 plus 1 is equal to 7, or it will give a septet. Septet, right? That is what we are going to observe. So, if you are looking at the ESR spectrum of this molecule, the ESR spectrum will look like this. Okay, 1, 2, 3, 4, 5, 6, 7. 7 peaks are there. All the 7 peaks are equally spaced, even though my drawing is not very good. Okay, so you will see a septet here, and if you are checking the coupling constant, means the distance between two adjacent peaks in the ESR spectrum, and that value will be equal to 0.38 millitesla. 0.38 millitesla. 38 millitesla. What was the coupling constant that we observed in the case of the methyl radical? That was 2.3 millitesla. Okay, and here it is 0.38 millitesla, much smaller coupling constant. Okay, and from here also we can calculate the electron density at the hydrogen. So electron density at the hydrogen rho is equal to A divided by R. A is the coupling constant. Here the coupling constant is 0.38 millitesla, that is equal to 0.38 into 10 raised to minus 3 Tesla divided by R. R is the intrinsic coupling for the unit density for hydrogen atom, and that is equal to 0.05 Tesla, right? And if you are calculating this, we can see that this is equal to 7.6 into 10 raised to minus 3 minus 3. Okay, it has no unit. Tesla and Tesla will be cancelled. So it is just electron density, the fraction of electrons that we can see in the hydrogen around the hydrogen nucleus. That is what this number indicates. Okay, so this is a rho, that is the electron density at the hydrogen nucleus, single hydrogen nucleus. So if you are counting the electron density at 6 hydrogen nuclei, we can calculate the electron density. Electron density at 6 hydrogen nuclei, that is equal to 6 into 7.6 into 10 raised to minus 3, and that is equal to 45.6 into 10 raised to minus 3, and that is like 0.0456, right? 0.0456, and that is equal to 4.5 percentage, 4.5 percentage, right? So electron density at a 6 hydrogen nuclei altogether is 4.5 percentage, or roughly we can say it is 5 percentage. Okay, so 5% of the electron density will be at the hydrogen atoms. So the remaining 95% of the electron density will be at the carbons, right? So 6 carbons, electron density at 6 carbons will be equal to 95 percentage. It means that each carbon will have a share of 16 percentage. Means the electron density at a single carbon is almost equal to 16 percentage. Almost equal to 16 percentage. Okay, that is what we can see from here. So the electron density at a single carbon is 16 percentage. So same calculations, the similar calculations we already carried out at the methyl radical. Okay, and now I hope you got an information, or you got some nice idea about the hyperfine structure observed in the ESR spectroscopy. And now let us come back to the methyl radical just to add a few more points, okay, just for your understanding. And the methyl radical, we have learned that in the case of the methyl radical, the electron density at the hydrogen atom Okay, that is 4.6 percentage. Each hydrogen atom or each hydrogen nucleus has an electron density of 4.6 percentage. That is what we got from the ESR spectrum. Okay, and that is why there is a coupling between the hydrogen and the nucleus. Okay, and if we are considering the molecular orbital theory of the methyl radical. Okay, from the molecular orbital theory, the methyl radical is a planar molecule like this. Okay, this is the carbon. Let me put that in the red level. This is the carbon, and we have hydrogens here. This is hydrogen, hydrogen, and hydrogen. Okay, and they are in a plane. So if you are making a triangle like this, we can make a triangle like this, and the carbon will also be lying on this triangle. So this is planar. Okay, this is planar. It's a single plane. So this is plane, single plane. Okay, and the radical electron will be in an orbital which is perpendicular to this plane. Okay, so the orbital will be like this. So perpendicular to this plane, there will be an orbital like this. Okay, there will be an orbital like this, and this orbital will be occupied by the single electron. Okay, and one lobe of this orbital is above the plane of the CS3 radical, and the other lobe is below the plane of the CS3 radical. And there is a single electron within this orbital, and that single electron is spread between two lobes. Okay, the lobe above and the lobe below. And if you are observing the electron density at this plane, you consider that this is the z axis, and the plane of the molecule will be the xy plane. So if you are looking at the electron density at the xy plane, the electron density at the xy plane will be 0, because for this orbital xy plane is a nodal plane. You already know about the nodal planes. Nodal plane. Okay, means in the nodal plane there will be 0 electron density. And you know that the hydrogen nuclei are sitting, or hydrogen nuclei are occupying the positions in this nodal plane only. And in that nodal plane, the electron density of the radical electron is 0. It means that from this molecular orbital theory, we have to assume that the electron density, means radical electron density around the hydrogen nuclei is something like 0, right? And that is very contrasting to our observation. If the radical electron density at the hydrogen nuclei is 0, then there will be no coupling between the electron and the hydrogen nucleus. And if there is no coupling, we will not observe a triplet, or we will not observe a quartet. But in experiment, we are observing a quartet, and a quartet with a coupling constant of 2.3 millitesla. That is what we are getting experimentally. So the assumptions that we are drawing from the molecular orbital theory are in contrast with the experimental observation. And how we can fit our assumptions with the experimental observation. That's a problem. If we are using only the simple molecular orbital theory, the simple molecular orbital theory is going to give a wrong results. Wrong result. The simple molecular orbital theory is going to tell you that there will be no coupling, and there will be no electron density at the hydrogen nuclei, therefore there will be no coupling. Okay, so the coupling constant will be 0, means you are going to get a singlet only. That is what the simple molecular orbital theory is going to tell you, and that is a lie. Okay, so we have to modify this simple molecular orbital theory in order to fit with the experimental facts. So how we can modify this simple molecular orbital theory? How we can explain the coupling in spite of the zero electron density predicted by the Monica orbital theory. So that's the question. So let us consider the medial radical like this. So this is medial radical. I am just redrawing it here. So this is the carbon. Here is the hydrogen, and here is the hydrogen. Okay, and these hydrogen, the carbon hydrogen bonds, I just indicated by a line. And the next carbon hydrogen bond I am going to indicate in a much complex way. Means I am going to draw the orbitals taking part in the bonding. So we have an orbital here, okay, and that orbital is overlapping with the orbital of the hydrogen. So here is the hydrogen nucleus. Let me draw that in the red. This is a hydrogen nucleus. Okay, and now let me draw the electrons in this species. Okay, so you already know that electron in carbon, carbon will have the 4 electron in its valence shell. So one, this is S, this is means it is a 2s orbital, and this is 2px, 2py, and 2pz orbital. So when the electrons are filling in this carbon atom, it will be like 2s2, then 2px, 2py. But for hybridization, it will be like this: 2s1, 2px1, 2py1, 2pz1. Okay, means 4 electrons are singly occupying the orbitals. Okay, so if we are considering these electrons, okay, these 3 electrons, if you are just considering the hybridization, these 3 electrons will make the sp2 hybridized orbitals, and the other electron will be perpendicular to the sp2 hybrid orbital, and each of these sp2 hybrid orbitals will be used for making the bonds. Okay, this is a trivial valence bond theory assumption. Okay, so if you are taking these assumptions into here, we can assume that all the electrons in the carbon have the spins in the same direction. Okay, all the electrons in the carbon have the spins in the same direction. So let me put this radical electron here first. This is a radical electron, and the radical electron is perpendicular to the plane of this CS3 radical, and this radical electron has this type of spin. Okay, this is the radical electron spin. Let us suppose that is the up spin, and then the other electron, this is 2pz radical electron. The other electron in the carbon should also have the same spin, means up spin. Okay, this is what we can just understand from here, from Hume's rule of maximum multiplicity. Okay, and then here, when we are coming to here, this electron, which is already shared with this carbon, the electron from the hydrogen, that should have a down spin. Okay, that is the Porous exclusion principle. It should have the down spin, because these two shared electrons should have a positive spin. This is up spin, and so this should be down spin. And the hydrogen electron has the spin down, and that since hydrogen electron has the spin down, then the hydrogen nucleus is expected to have the spin up. Okay, so the hydrogen nucleus is expected to have the spin up. Okay, this is what we are assuming here. See, the hydrogen nucleus is having a spin up here because of the communication from here. It is communicated from here to here, it is communicated to here, from here it is communicated to here. Okay, there is a chain of communication. Okay, and the nuclear spin actually is determined from a remote space, or this radical electron is determining the nuclear spin at a remote place, even if the nucleus is not under the direct influence of, not not at the vicinity of this radical electron. This radical electron is still able to communicate to this nucleus. Okay, and this is called the configuration interaction. The configuration of the spin is determined from a remote place. Okay, or the configuration at a remote place is being determined by this electron spin. So this is the configuration interaction. Configuration interaction. And this configuration interaction was not a part of the simple molecular orbital theory, and that is why the simple molecular orbital theory is going to give you a wrong results when we are predicting the coupling constant of the hyperfine structure of the ESR spectrum. But if you are incorporating this configuration interaction also in the molecular orbital theory, then you will get decent results. So the molecular orbital theory incorporated with the idea of configuration interaction is going to give you better results, which will give you good accurate results, almost accurate results for the hyperfine structure of the ESR spectrum. Okay. So actually what we have to now think, philosophically speaking, some time ago we were defining the electron density as the physical density of the electron. Okay, we were defining the electron density as the physical density of the electron. Means whenever we speak that there is some electron density around the nucleus, we mean that surrounding that nucleus there is a physical presence of the electron cloud. That is what the physical density of the electron. And from that mere idea, we have to move away to another idea. Or just by saying electron density, we have to actually understand like it is not just the physical density of the electron. It is the influence of the electron, influence of the electron at a remote place. That is what we have to understand from the electron density. So from the mere idea of the physical density of the electron at a remote place or at a particular location, we have to think about the influence of an electron at a remote place. Okay, this is the idea that we have to incorporate while modifying the molecular orbital theory in order to predict the ESR spectrum or hyperfine structure of the ESR. I hope you got some idea of the hyperfine structure of the ESR spectrum. And if you have any doubt, don't hesitate to ask me. I will be happy to answer your questions. And thank you for watching and stay tuned.